The purpose of this AP Physics Final Project is to incorporate 13 units of physics into 10 sequential events that result in a Winter Olympic-themed luge and curling course. By completing this project, we demonstrated our proficiency over these 13 units that we have covered this year.
Our flat and slightly rounded curling stone had to travel a meter vertically and a meter horizontally while sliding through the 3 bank turns, all while not exceeding 45 degrees. We fulfilled these requirements through persistence, trial, and many errors, and advice from our experts, also with the use of over 40 hot glue sticks. Okay, now let's go see the project.
We're here! For our curling stone, we use a 3-volt coin cell that's usually found in watches. At 1, force, motion, and work. For our procedure, we turn on the motor, and then the platform is pulled up through the pulley, and then connected at our ramp with magnets.
For the calculations for our first unit, which is force, motion, and work, we have 2 simple calculations. First, we have force equals mass times acceleration, in which we took the total mass of our platform that is being lifted in the elevator times acceleration due to gravity, which is 9.8 meters per second squared. Force ended up being 1.0094 newtons. For work, which is mass times acceleration due to gravity times height, we have, again, the weight of the platform in kilograms multiplied times acceleration due to gravity times the height of the entire system, which is 1 meter. And the answer for work was 1.0094 joules.
Our second event was electricity, and for this one we turned on the motor, which completes the circuit inside of the motor using the AA batteries. This causes the motor to turn, spinning the spindle and pulling the string.
For Unit 2, electricity, we have 2 equations. First, we have Ohm's law, which is intensity equals voltage divided by resistance. And we did 3 volts divided by 1.72 ohms, which we found using an ohmmeter. And intensity ended up equaling 1.744 amps. The second equation we have is for power, and power equals intensity times voltage. So we took 1.744 amps times 3 volts to discover that the power was 5.232 watts.
Event 3, friction, we put the steel battery on our plastic Hot Wheels ramp and recorded the time it takes for it to pass each interval.
So for Unit 3, which is friction, here are some of our calculations. So first we found velocity, which is delta x over delta t. And for delta x we had 0.25 meters, and for delta t we had 0.63 seconds. And when you divide those, you got 0.3968 meters per second. Next we use that to find our acceleration, which is delta v over delta t. And for delta v we had 0.3968 meters per second, which we just found over there. And then for time, we use the same time, which was 0.63 seconds. And when you divide those, you get 0.6298 meters per second squared. Then we use that to find the force. We found the force for plastic friction, 0.006 kilograms for our mass, and multiplied that by 0.6298 meters per second, which is what we found for acceleration. And when you multiply those together, you get 0.00378 kilogram meters per second squared. And next we found the coefficient of friction. So we took the plastic friction and set that equal to the coefficient of friction times force normal. And so we plug in 0.00378 newtons equal to coefficient of friction times 0.06 newtons. We found that to be 0.063.
To create our position versus time graph, we used a power fit for all of our data. Our graph suggests that distance is directly proportional to time. The final mathematical formula is x equals 0.398t to the 0.8498 power. To get our velocity, we derived our previous equation and got v equals 0.339t to the negative 0.1805. We then calculated all of our data points and plugged it into a velocity versus time graph. In this, we used a power fit as well. The graph suggests that velocity is indirectly proportional to time. Our final specific mathematical model came out to be v equals 0.3960t to the negative 0.1076. The graph suggests that acceleration is indirectly proportional to time. The final mathematical model is a equals 0.1485t to the negative 0.7368. There is possible error in the shape of the battery and the ramp, as the acceleration is not negative on the graph, despite that it should be. The acceleration does, however, seem to be decreasing.
Our fourth event is constant velocity, which, like our friction event, we recorded the time it takes to pass each interval.
For the evaluation of data for constant velocity, and for the linear first graph that we did, which was position versus time, we decided that the distance was directly proportional to time. And the final mathematical model for this graph is x equals 0.6894 meters per second times time minus 0.01601 meters. For the evaluation of data for our second graph, velocity versus time, we decided that the final mathematical model for this graph is velocity equals 2.232 times 10 to the negative 15th meters per second squared, which is really close to 0, times t plus 0.6894 meters per second. And because the slope is supposed to be 0, so that the final velocity is just 0.6894, and our slope is very, very close to 0, it works out.
Event 5 is constant acceleration, in which we let the marble pass down the ramps and we record the time it takes for it to pass each interval.
So for constant acceleration, we took the total force equals force of gravity plus force due to friction. So for force of gravity, we set that equal to mass times acceleration, and for our mass we had 0.005 kilograms, and we multiplied that by our acceleration, which was 0.1763 meters per second squared. And from that we got 0.0008815 newtons. And for our force due to friction, that was equal to 0. So our total force ended up equaling 0.0008815 newtons.
For event 5, constant acceleration evaluation of data, we had 3 graphs: the position versus time graph, the velocity versus time graph, and the acceleration versus time graph. For the position versus time graph, the distance was directly proportional to time. The final specific mathematical model for our position versus time graph was x equals 0.3653 meters per second times t to the 1.328 power. For our velocity versus time graph in our constant acceleration unit, the velocity is directly proportional to time. The final specific mathematical model for that graph is velocity equals 0.1763 meters per second squared times t plus 0.1690 meters per second. For our acceleration versus time graph, it is quite simply just a straight line. The final specific mathematical model for the acceleration versus time graph is acceleration equals 0 meters per second times t plus 0.1763 meters per second squared.
Our sixth event was projectile motion momentum. For this one, a marble rolled down a cardboard track and hit another marble, which fell into the cup, and we measured the horizontal and vertical distance. Sixth event was projectile motion and momentum. And for this one, we found the average velocity, which is equal to 0.01 meters over 0.22 seconds plus 0.01 meters over 0.35 seconds plus 0.01 meters over 0.24 seconds, and all of this divided by 3. When we calculated this, we found it to equal 0.386 meters per second. Next, we found the momentum, which equals mass times velocity. So for our mass, it was 0.005 kilograms, and our velocity was 0.0386 meters per second. And when we did the calculations, we got 1.93 times 10 to the negative 4.
For our projectile motion unit, we have two graphs, one vertical position versus time graph and one horizontal position versus time graph. The final specific mathematical model for the vertical position versus time graph is x equals negative 2.67 meters per second times t to the 2.032 power. For our horizontal projectile motion graph, the final specific mathematical model for this horizontal position versus time graph is x equals 0.091 meters per second times x minus 0.000523 meters.
Event 7, uniform circular motion, involves mousetrap. For this, we set the marble up at the top and let it go down our track, in which it falls here and sets off the mousetrap.
Our seventh unit was uniform circular motion, and for this one, we found the velocity by setting it equal to 2 pi times radius over time. So our radius was 0.045 meters, and our time was 0.433 seconds. And when we did the calculations, we ended up getting 0.653 meters per second. Our eighth event was waves and sounds. For this one, we rolled a marble down our track again and triggered the mousetrap, and we recorded the angle and the time it took for it to go, and we also recorded the amount of hertz.
For our 8th unit, we had one formula. We had to solve for the wavelength. So we took velocity divided by frequency, which is 13.29 meters per second, divided by 121 hertz. The wavelength ended up equaling 0.110 meters. Okay.
Our 9th event was advanced rotational motion. For this, we recorded the distance the car traveled down this Hot Wheels ramp, the diameter of the wheel, and the time it took for it to go down.
9, advanced rotational motion, we have several formulas. We had to find circumference, which is 2 pi r, so we took 2 times pi times the radius of our wheel on the toy car, which is 0.005 meters, and it ended up being 0.01 pi. For rotations, it's distance divided by circumference. So we took the length of the track that the car rolled down, which is 0.53 meters, divided by the circumference that we just found, which is 0.01 pi. The answer to that ended up being 16.87 rotations. Next, we had to find angular velocity, which is the number of rotations divided by the change in time. So we took 16.87 rotations divided by the time it took for the toy car to go down the entire track, which is 0.45 seconds. And the angular velocity ended up being 37.49 rads per second.
Our 10th event is simple harmonic motion. For this one, when the Hot Wheels car goes down the track, it closes the scissors and it releases the first golf ball, which hits.
For simple harmonic motion, we created a Newton's cradle out of ping pong balls. To record the data, we used a slow motion video and timer and recorded the maximum and minimum positions of the first and last ball of Newton's cradle. We created a cosine model for our position versus time graph, in which our final mathematical model was x equals 0.04319 cosine 15.40 t plus 0.07982 minus 0.098 meters. We chose a cosine curve because the motion starts at its minimum value. To create the velocity versus time graph, we derived the position formula. For our final specific mathematical model, we got v equals negative 0.6651 sine 15.40 t plus 0.0795 plus 1.733 times 10 to the negative 5 meters per second. The sine model shows that at the maximum position, the velocity is 0, and at the minimum position, the velocity is at its maximum. Finally, to get our acceleration versus time graph, we derived our velocity equation. Our final mathematical model for acceleration was a equals negative 10.24 cosine 15.40 t plus 3.221, all minus 0.0003553 in meters per second squared. This model shows that acceleration is at a maximum when the position is at its maximum, and a minimum when the position is at a minimum.
Where we took 3 volts divided by 1.72 ohms, which we found using the ohmmeter.
Had to travel a meter vertically and a meter horizontally while sliding through the 3 bank turns. All while not.
Next, we had to find anglerfish.
Distance, trial, and many errors, and advice from our experts. Also with the use of over 40 hot glue sticks.
Darn you, car!
Wait, what is this called again? Rotations? The number of rotations. Go see
Now
our
let's
project.
go see the project.
No. Divided by resistance. So here we took intensity equals 3 volts, which we discovered was